So we'll start lecture 3 today, where we'll be talking about sigmoid neurons, gradient descent, feed-forward neural networks, and representation power of feed-forward neural networks. Right. So before I begin, just a quick set of acknowledgements. So for module 3.4, I have borrowed ideas from the videos of Ryan Harris on visualizing backpropagation. These are available on YouTube and linked on the slide here. And for module 3.4, I have borrowed ideas from this excellent book, which is set in the footer, which is again available online. And I'm sure I've taken ideas and been influenced by material elsewhere. So I apologize if I have failed to acknowledge them. And if you find anything that I should acknowledge, please let me know. I'll add it to the slides. Okay. So let's start with the first module, which is on sigmoid neurons, right? So where are we right now and what is the story ahead, right? Let's just get that picture clear and then we can start. So frankly, enough about Boolean functions, right? So the last lecture, the entire thing was about Boolean functions, where we were looking at functions y is equal to f of x, where both x was Boolean and y was Boolean. Of course, when we were looking at perceptrons, we said that real inputs are allowed. But for most of the discussion, we were focusing only on Boolean inputs, right? So I want to move away from there. And where do I want to move, right? So we want to look at arbitrary functions of the form y is equal to f of x, okay, where x belongs to Rn instead of 0, 1, or instead of like Boolean, and y also belongs to R, right? So what that means is that both x and y contain real numbers, right? And so now let's look at an example of this, right? So what do I mean by I want to move towards these problems? So I'll take my favorite example, which is the example of trying to find whether I'll find oil at a particular location, or what is the quantity of oil I can find at that location, and that would drive my decision on whether I should set up a drilling station there or not. It's a practical problem, and I could imagine that such a decision would depend on several factors, right? So let's imagine I'm looking at a location inside the ocean, right? And I want to decide whether this is worthwhile investing in setting up a drilling station there, which means I want to know the quantity of oil that I can mine from there, right? And I would base my decision on several factors. So say salinity could be one, right? Then I could look at the density of the water there, right? Sorry, this pen is not really working well, but I'll just go ahead. So salinity, density, you understand what I'm saying. Then maybe I can look at the pressure at that location. I could look at the temperature at that location. I could look at the marine diversity at that location, right? So all of these are real values, right? So all of these belong to R. All of these are real values, and I might base my decision on n such different factors, right? And this we have been discussing for a while, that whenever I take decision, I consider a lot of inputs, and now I'm talking about n inputs. Each of them is a real number. So this vector that I'm looking at here is a vector which belongs to Rn, right? So that's the idea now. So that's what I meant by this, that x belongs to Rn. And now what is it that I'm trying to predict in this case? I'm trying to predict a y which again belongs to R, right? So y again belongs to R because y is again a real number. I'm trying to predict the quantity of the oil that I can get from that location, right? So this is a real world problem, and you could think of various such real world problems, right? So another example could be if you want to decide what is the interest rate that you should set for a particular customer, right, as a bank. And this often depends on the past history of the person, whether he'll be able to pay at a certain rate, pay back the capital and so on, right? So you might have factors like what is the salary, what is the family size, right? What was the last loan that that person had taken, how many years that loan was repaid in, what was the interest rate for that loan, was there any defaults, and all of these you can see are real numbers. And then the output is also a real number, which you want to decide an interest rate, maybe something between say 5 to 20%, right? That's what you want to decide. So this is another problem, right? So these are the kind of problems that we are interested in dealing with, where your inputs are real numbers and your outputs are also real numbers, right? And we'll take this idea further. Well, we'll start later on in the course talking about images, right? And even if you look at images, what is an image? If you look at a 100 cross 100 image, these are pixel values which tell you some colors, right? So these are all again real numbers, and based on these real numbers, which is a very high dimensional vector, because you're looking at a 100 cross 100 vector now, and I can just flatten it out and I'll have 10,000 values which correspond to the pixel values, right? So let's assume it's only gray and white images, right? So you will have certain pixel values there, and this is a 100 cross 100 dimensional vector, and based on this you might want to predict a certain y, right? So this is again of all of these are cases where your inputs are real and your outputs are also real, and you have a high dimensional input where I'm just calling it as Rn, which is an n dimensional vector, right? So this is the situation that we want to deal with. Now, given this situation or given these kinds of problems, what is our quest, right? So our quest would be, just as it was on the case of perceptrons when we were dealing with, or in the last lecture when we were dealing with Boolean functions, we wanted to know if we can have a network which can exactly represent such function, right? And my definition of exactly represent was very clear in the case of Boolean functions, where I was saying that I know what the truth table of this function is. And then when I take an input, say 0, 0, right? And I pass it through the network, I should get the same output as is decided by this truth table, right? That was my definition of exactly representing the function. And then we also moved on to slightly more real worldish, where we said that I would have been given data where I would have different inputs, right? And the output for that input, right? And if this data was linearly separable, then I should have a network such that it takes any input from this training data and it gives me the same output as is given to me in the training data, right? So in the training data, I'm given these x, y pairs, right? And then I have a network. I pass this x through the network and it predicts a y. I'll just call it y hat. So I wanted the y hat and the y to be same. And that's what it means by this network can exactly represent the function, right? Now, I'm just loosening that definition a bit. I'm saying that can I have a network which can approximately represent the function, right? Which means what? That I want y hat to be approximately equal to y. Why this approximately, why not exact? We'll come to that later on, right? For now, if you want to assume I want something which is exactly equal, that's also fine, right? But I'm just going to be a bit more relaxed in this lecture, right? I would just say approximately is also fine, right? So that is what I want. Can I construct a network such that when I give this real valued inputs, right, and I get a prediction from the network, that should be as close to what is given to me in the training data, right? That's what my quest is going to be. Okay. And just to make it more concrete, so in the oil mining example, there are already many locations where drilling stations have been set up and oil is being mined for many years, right? So I know what was the quantity of oil mined from those stations, and I know what their X characteristics were, right? So what did the salinity, what was the pressure, what was the density, what was the temperature, what was the marine diversity, all I know, right? So what I want is a network such that when I feed any of these X's to the network, the y predicted by the network should be very close to the y that I actually have, right? So that is what our quest is going to be. I'm just defining the problem. I'm not telling you a solution at all, right? This is just about what the story ahead is going to be. Okay, so let's move ahead from here. I better delete a few of these things. So before answering the above question, right, we'll first have to graduate from perceptrons to sigmoid neurons, right? So that's the first thing that we're going to do. So recall that when we are dealing with perceptrons, a perceptron fires when the weighted sum of its input is greater than the threshold, right? And this, we had this thing that theta is equal to minus W naught, right? Because we move it to the other side of the equation. Okay. So this is what a perceptron, like a single input perceptron looks like. I have an input, I have a certain weight associated with the input, I have the output, and then I have the weight, I have the bias or the threshold, which is say, the minus of the threshold is 0.5, so minus of W naught is 0.5, right? And now this neuron, this perceptron will fire if the weighted sum of my input, which is just W1 X1 in this case, is greater than 0.5. Now I'm going to say that this logic used by a perceptron is actually very harsh, right? Now what do I mean by harsh? Harsh is not like a mathematical term. So what do I mean by that, right? So let us return to our example of deciding whether we would like or dislike a movie, or whether we would like or dislike a movie, right? Now, let's say we are basing our decisions only on one input, which is the critic's rating, and the critic's rating is something between 0 to 1, right? On a scale of 0 to 1, a critic has given some rating, and we look at that and decide whether we want to watch the movie or not, right? Now, if the threshold is 0.5, and let's assume that the weight is 1, because there's only one input, so it doesn't matter what the weight is, right? We'll just give it 1. And what now in this case, when the threshold is 0.5 and the weight is 1, so what about the case when the critic's rating was 0.49? The output of the network would be dislike, right? Because 0.49 is less than the threshold, so I will not like the movie. But now if I had a movie for which the critic rating was 0.51, then my output would be like, right? And this is why I say that this is very harsh, right? This is not how you would take decisions in real life, that 0.49 is not like, but 0.51 is like. I mean, there's very little difference between these two, right? I mean, you wouldn't base your decisions like that. What you're looking for is something more smoother than this, right? Which calibrates that, okay, 0.49 is good, 0.51 is slightly better, right? It should have that calibration, right? So that is missing. It's just very harsh. That, and I'll show you a figure on the next slide which will make this very clear, right? And that's the point I want to make. That is not a characteristic of the problem that you have chosen. It's not that about movie ratings, or it's not about the way I have chosen this threshold or the examples that I have given. It's the nature of the function itself, right? And I'll tell you what I mean by that. So this is what the perceptron function looks like. So what I have here, this is my z-axis, okay? So on this axis, I have z, where z is the weighted sum of the inputs, okay? So this quantity I'm calling z, which we have seen is the weighted sum of the inputs, okay? And this is my threshold. And I know that when z crosses the threshold, my output is going to be 1. And when z is less than the threshold, my output is going to be 0. So there is going to be this sharp increase at 0.5. And that's what was happening in our example. Till 0.49, I was not so upbeat about the movie. The moment it crossed 0.5, I said, oh, okay, like this movie. Right? So this is the nature of the function itself, where if you take this weighted sum and it crosses a threshold, you say 1. If not, you say 0. So this if-else nature is what is bringing this discreteness, right? What is saying that, okay, it will suddenly become 1, right? So it's the nature of the function itself. This is a step function, right? And there will always be the sudden change whenever you have a threshold function, right? And as I said, like for most real world applications, we don't want this. We want the decision to be much smoother, where the difference between 0.49 and 0.51 is not yes and no, right? It should be something more smoother than that, right? So let's see how do we get there. Now this looks like a smoother version of the function, right? So what is happening here? Again, this is my z-axis, okay? And this is what z is, right? And now I have not explained what this function is. I have not given you the formula. For the perceptron, I had given you a formula that y is equal to 1 if something, y is equal to 0 something. I have not given you a formula. But for now, we'll just appreciate that this looks more realistic, right? That it's not suddenly changing its decision. It's gradually moving from 0 to 1, right? It's not like very sharp as was in the case of the earlier function, right? So to get this kind of an effect, we'll now introduce what is known as the sigmoid neuron. And sigmoid function, the function sigmoid is like a family of functions, and here's one member from that family, which is called the logistic function. Later on in the course, we'll see the tan H function, which is also a member of this family, right? And let's see what is happening here. So this is a quantity which is familiar to us, right? This is the weighted sum of the inputs and the threshold. Okay, this quantity is familiar to us, and we have been writing it as summation I equal to 0 to n w naught x naught, right? So it is the same quantity that we have been writing, and this quantity we have actually been writing as w transpose x, if you remember, right? Where x is the vector from x0 to xn and w is a vector from w0 to wn, right? So this is just the dot product, right? So the quantity that I have underlined is just this quantity that we have been dealing with so far. Okay, now let's look at this function a bit carefully. So what happens when W transpose X tends to infinity? Okay, so this is as I go along this axis, this is where W transpose X will start tending to infinity, right? Because Z is what I've defined as W transpose X, right? So what would happen as it goes towards infinity? If I substitute the value infinity here, right? So it is 1 over 1 plus e raised to minus infinity, right? That would be 1 over 1 plus 1 raised to e raised to 1 by e raised to infinity, right? This would become 1 over 1 plus 1 over e raised to infinity, right? That's what this would be. And this term would become 0. So you'll just have 1 over 1. So that would be 1. And that's exactly what is happening here. As the value of this W transpose X is increasing, the function is approaching 1, right? And what would happen if W transpose X tends to minus infinity? This would become 1 over 1 plus infinity, right? So in that case, the denominator would become infinity. So 1 over infinity would be 0. So as I go in this direction, so as I go in this direction, which is minus infinity, my function starts tending to 0, right? So that's why this behavior is there. And now again, let's just do one more thing. If W transpose X equal to 0, if I substitute that value, then I get 1 over 1 plus e raised to 0, right? And that would be half, right? So that's what you are seeing here. Okay, yeah. So that's what is happening here. So for this discussion, just let's assume that W0 was 0, right? So that this so that all of this is in sync, right? So that this disappears and all of this falls in sync. If you have a W0, you can have a similar explanation. It's just that the graph will move a bit, right? So I'll leave it for you to figure that out. But what is the important thing is, how do you get this S shape? At large values it saturates, at small values it saturates, and it goes smoothly from the small values to the large values, right? So that's what is happening here, and we no longer see this sharp transition which we are seeing in the step function earlier, or the perceptron function, right? Let's just delete this. Also, the output Y is no longer binary, right? But it's a real valued output. It's not 0 or 1. Many values between 0 and 1 are possible. Now, the other interesting thing about this function is that since the values are between 0 and 1, right? So what is the other quantity of interest which lies between 0 to 1? Probability, right? So probabilities lie between 0 to 1. So now this output of the sigmoid function we could interpret as a probability. So now when it gives the value 0.49, I can say that there's a 49% chance that I'll like the movie. Earlier I was saying that there's a 0 chance I'll not like the movie. When it outputs a value of 0.51, I can say there's a 51% chance that I'll like the movie. And now this makes sense, right? The difference between 49 to 51% makes sense, right? Earlier it was 0 and 1 when it was 49% and 51%. So that harshness has disappeared now, and more importantly, I can now interpret these values as probability. And this is something very important, because in most modeling problems, that is what we would want to do, that you have to predict a certain binary value and you would like to predict it as a probability, that this is not harsh 0 and 1, but this is a 49% chance of finding oil there. There's a 49% chance that this person will not return the role. And then as a domain expert, you can decide whether you want to invest in that or not, right? Okay. Okay, so that's what it is, and this is how the two functions look like. Very similar, right? The inputs are actually similar, as you can see. The weights are also available. You have an output. You know that these are all real values. You know that the output is real value, right? In fact, in the perceptron also, you could have had real values. It's just that we were only looking at Boolean. But the main difference is in this function here, right? You have the sigmoid function here, and you had the step function there. And that step function is obvious because of the formula that we were using, which is this: y is equal to 1 if something, y is equal to 0 if something. So 0, then go to 1, right? Whereas now you have this smoother formula, which we just saw on the previous slide, which is just 1 over 1 plus exponent of something, right? And that gives you this smooth function, right? And even if you look at the plots, then you see that the perceptron function is not smooth and hence not differentiable at this sharp change at the value where it changes, whereas the sigmoid function is smooth, it is continuous, and it's differentiable. So now why do we care about continuity? Why do we care about differentiability? So for a large part of this course, calculus is going to be the hero, right? So whatever algorithms that we study today and going forward in the next few lectures, everywhere calculus would play an important role. In particular, derivatives would play an important role, and hence it's important that the functions that we deal with are differentiable, right? So that's where I'll leave it for now. I'll not delve further into it, and you'll get to know why differentiability is important, because I'll soon start taking derivatives of something, right? And if I'm taking derivatives of something and everything in the calculation is not differentiable, or if all the functions involved are not differentiable, then you can't take the derivatives, right? So that's why it's important to have differentiable functions, and that's why we have, it's good to have the sigmoid neuron with us. Okay.